And by the way, this video discusses on how we can be able to present the number in a scientific notation, or what you call it as in a standard notation, and how we can get it back to normal from scientific to normal as well, and how we can make use of what we call them as the prefixes in converting the units from one unit to another unit, basically a linear scale and area scale as the volume scale. So we should have to discuss all these things. Just have to pay attention, take note of whatever you deserve to have. So keep that in mind. And we know that we have several examples of physical quantities. If we say a physical quantity, it is a quantity that can be measured. And we have the physical quantities like time, we have the distance, speed, we have the temperature, pressure, and some other examples you may think about. But sometimes we may happen that we have measured the very largest number or the very smallest number. Let's say you may happen to have a number like, let's say 2,500, let's say seconds. This is a very largest number. And let's say if we have, let's say 26,000, let's say meters, and this is a typical largest number. It can be a million numbers, or let's say we can have about, let's say 1 million seconds. That is cool. So this is also the very largest number. And I would like to look at how we can have to present this number in the shortest way, but you don't have to change the meaning. And let's say we have the very smallest number given as, let's say 0. Let's say 6 should be 0, let's say 6. How should you have to present this number in a scientific notation? Now, if we say a scientific notation, this is the shortest way of presenting the largest numbers as well as the smallest numbers, but it should not have to change the meaning. That's what we call it as the scientific notation. For instance, let's say we have measured a number given as n, and let's say it is the very largest number or the very smallest number. So how can we be able to present this number in a scientific notation? Now this number will be given as a times 10 to the power should be n. So this is how the number is presented in our scientific notation, where n shows the number of steps, and the whole of this one, 10 to the power n, shows the multiples of cells. The whole of this one shows the multiples of cells, and where a is the number ranges from, let's say, where a is the number ranges from 1 to, let's say, should be 9. So should be that, a can be a number, let's say 1 up to 9. It can be less than 1, or it can be, let's say, it should be a more than 9. So that's how we should have to understand about presenting the number in scientific notation. Let's say we have a number given, let's say 2,000. So how should we be able to present the number 2,000 in a scientific notation? The first thing to understand is that, let's say if we have a number given as 5. So given a number given as 5, this is the same as having as 5 point. It is the same as that. Let's say if we have a number, let's say 1,000, this is the same as having it as 1,000 point. So if that is the case, having 2,000, it is the same as having it as, should be 2,000 point. Now we need to displace actually a decimal point until we reach at the position of, between the last but one value, until we reaches at the position of last but one value. Now for this case, should be until we reach at the position before last but one value. And for this case, it means the decimal point will be displaced in this direction, and until it reaches here. So have it as 1, 2, 3. The decimal point will be pressed there. Therefore, we'll have it as 2.000 times 10 to the power. How many steps have we actually? How many numbers have we actually passed we have 3 numbers, therefore have it as positive 3. So having this one, it is the same as having it as 2 times 10 to the power positive 3. So this is what we call as the scientific notation. And let's say if we have a number given, let's say 2600. Let's say that is the case. Principle remains the same. We will have to displace, we are having 2600 being given as 2600 point. The decimal point has to be displaced until we reach as the number just before the actually a last but one value. Have it as 1, 2, 3. Now we'll have it as 2.600 times 10 to the power positive 3, since the decimal point has passed 3 numbers. So in this case, this is the same as 2.6 times 10 to the power positive 3. So that's how we can have it in scientific notation. Let's say if we have a case whereby you have, let's say, 9,500. Should be 95,000 rather, should have that one. So how should you have this number in scientific notation? Principle remains the same. Having 95,500, this is the same as 95,500 point. The point has to be displaced. We'll have that one as that. Therefore, we'll have 9.5000 times 10 to the power positive 4. Since the decimal point has displaced about 4 numbers, 4 digits. Of course, this is the same as 9.5 times 10 to the power positive 4. So this is how we can have it. And let's say if we have something about, let's say, 200, should be, let's say, 2500, let's say 600. Let's say we have this typical number, that is 2,500,000 and 600. How should you have to present this number in scientific notation? Principle remains the same. Having this number, it is the same as 2,500,000, 600 point. We have to displace about some steps. It's about 60 steps. Therefore, have it as 2.500,600 times 10 to the power positive 6. So that's how we can have it. So since the zeros are at the end, this is the same as having it as 2.5006 times 10 to the power positive 6. So that is the number in the scientific notation. What if, let's say, we have a sort of, let's say, 2562711? So how should you have this in scientific notation? Principle remains the same. We have 2562711 point. Now the decimal point has to be displaced about some steps until it reaches there. We'll have it as 2.562711 times 10 to the power. We have 1, 2, 3, 4, 5, 6. So have 6 there. So that is. And whenever the decimal point has been displaced towards the negative direction, the value of n should be the number of steps are given as the positive, and the positive n represents the largest number. So in all cases, if n is positive, it means it is a largest number. What if we have, let's say, this kind of a case? Let's say have 0.526, let's say 1. Now how should you have this number in scientific notation? So back to the actually a case of the scientific. If we have, let's say, a number n, in our scientific notation is the same as a times 10 to the power n, where a is the number which cannot be negative or cannot be a number that is ranges from 1 should be from 1 to actually 9. In other words, a can never be something above 9, and a can never be something below actually 1. So if that is the case, we should have to keep that in mind. So therefore, we have to displace the decimal point towards this direction. But now, since the value of a should not be a number greater than 9, it means the decimal point has to be displaced at this point. So have 1. So since the decimal point has passed about the single number, we'll have it as 05.261 times 10 to the power negative 1, since the decimal point has passed about a single step. Of course, this is the same as having it as 5.261 times 10 to the power negative should be 1. Whenever the decimal point is going towards this direction, it is more associated with having the negative step. So that simply shows that it's a smallest number. Let's say if we have 0.0025. Now, how should you have to express this number in scientific notation? Now, first thing you should have to understand that the decimal point has to be displaced towards this direction. But now, since all these are the zeros, the decimal point will have to pass all those zeros. We'll have 1, 2, until we reaches a number other than 0. So the decimal point will be displaced here. So in that case, we'll have it as 0.002.50 and times 10 to the power negative 3. Since the decimal point, by the way, you should have this. And since the decimal point has passed about 3 steps to the right, and this is the same as having it as 2.50 times 10 to the power negative 3. So that's how you can have that one. How about, let's say, if we have a case like this? Let's say if we have 0.0000005. So how do you think we should have to express this in scientific notation? So all these values are zeros. We should have to pass them all until we reaches at the point where we have a number other than 0. So we have 1, 2, 3, 4, 5, and 6 here. Now the decimal point will be pressed here. So we'll have it as 0, 0, 0, 0, 0, and a sort of 0. 5 point, you can have 0 times 10 to the power negative 5. Of course, this is the same as 5.0 times 10 to the power negative 5. So this is how you can have it in scientific notation. So keep that in mind. And also try this at your own time. Let's say if we have a number given as 21,250. How should you have that in scientific notation? Let's say if we have 0.01111. How should you have that run as well? Let's say should be 100,000. So how do you think we can have that in scientific notation? And what if, let's say, we have should be 6, or it should be 2, 3, 4, and that divided by, let's say, should be 10,000. How should you have that in scientific notation? And also, here's the task for you. How can we express a number back to normal from a scientific notation to normal? Let's say if we have a number given as 2.766 and times 10 to the power, let's say, negative 2. So how do you think we should have to express this number back to normal if that is the case? Now, having a negative power, it means this is the smallest number, and the decimal point has to be displaced towards this direction. So if that is the case, let's represent this number only. We have it as 2.766. Now, since we have a power given as negative 2, it means we have to displace the decimal point about 2 steps towards this direction. So in that case, we'll have it as 1, and we'll have 2, and the decimal point will be placed there. Therefore, we'll have it as a point. We'll have it as a 0.2766. In of which, having this one, it is just the same as having that 0.02766. So that's how you can have it in normal. And what if, let's say, we have this kind of a case? Let's say if we have 2 times 10 to the power negative 5. How should you have to express this number back to normal if that is the case? So having negative 5 simply means that it is the smallest number in which the decimal point has to be displaced towards this direction. So keep in mind that having just these two, it is the same as having it as 2.0 times 10 to the power negative 5, and of which you have it as 2.0, and since we have negative steps, it means we have to move towards this direction to displace the decimal point, and therefore have 1, have 2, 0, 3, 0, 4, 0, and 5, 0. We'll have the decimal point here. We'll have it as a point 0, 0, 0, 0, 2.0 should be that of 2, have 0 here, and this is the same as having the 0.0000020. So this is how we can have the number in normal notation, as you can see there. And how about, let's say if we have this thing of, let's say 2.5 times 10 to the power, let's say negative 10. So how should you have that back to normal? Let's say if we have 1.6 times 10 to the power, let's say negative 5, and let's say we have 2 times 10 to the power, let's say negative 7. And think about this one as well. Let's say if we have 8.77 times 10 to the power, let's say negative 4. How about, let's say if we can have that of 3.6666 times 10 to the power, let's say negative 5. So try to look at how we can have that. And how about, let's say if we have something like this. Let's say if we can have a number given, let's say 2.6, and let's say times 10 to the power, let's say 5. So how do you think we should have this kind of a number? Now, as you can see, this is actually a very largest number because of having the positive power there. So therefore have it as 2.6, and since the power is positive, it means the decimal point has to be displaced towards this direction about 5 steps. Therefore have it as 2 point, have 6, have 1, 2, 3, 4, and 5. So have it as 26, 0, 0, 0, 0. That is 260,000. So that's how you can have it normal from notation, from scientific notation. And let's say if we have, let's say 9.667, let's say times 10 to the power, let's say it should be 7. So how should you have this number? So since it is a positive power, it means that's the very largest number in which the decimal point has to be displaced towards that direction. Now in the sense that we have it as 9.667, and now have 1, 2, 3, 4, 0, 5, 0, 6, 0, and 7, 0. That is now 96, 6, 7, 0, 0, 0. That is how we should have. And at the own time also try to have the following in a normal notation. Let's say if we have 6.111 times 10 to the power positive 10. And let's say we have 9.6711 times 10 to the power, let's say 5. And also think about this one as well. Let's say if we have, should be 1.781 times 10 to the power positive 4. So how should you have that back to normal as well? And let's say if we have something about 7.66 times 10 to the power, let's say positive 12. So try to have that number in a normal notation. So now let's be talking about what we call as the prefixes. We understand that given a number n, the number n is represented as a times 10 to the power n, as this is a scientific notation. But now sometimes the multiple of zeros can be presented using what we call them as prefixes. So prefixes, these are the Greek actual letters. These are the symbols of the Greek actually letters that we actually represents the multiples of zeros. And the good examples of the prefixes, we have the following. So prefixes, these are the alphabetical, should be the Greek actually letters, should be, these are the Greek actually letters that we use to represent the multiples of zeros. We call them as the prefixes. In the good examples we have the likes of, in the good example of the prefixes we have the likes of, we have Dela, and a Dela has the symbol of a capital letter D, and that is given as times 10 to the power positive 12. And we have what we call as the Giga, and it is as symbolized as the capital letter G, which is at times 10 to the power positive 9. And we have what we call as the Mega, and which is symbolized as the capital letter M, that is given as times 10 to the power positive 6. And we have what we call as the Kilo, symbolized as small letter K, and which is given as times 10 to the power positive 3. And we have what we call as the Cent, and that is symbolized as the small letter C, which is given as times 10 to the power negative 2. And we have what we call as the Miri. So Miri is presented as the small letter M times 10 to the power negative 3. We have the likes of Micro. So Micro is given as Mu, which is given as times 10 to the power should be negative 6. We have the likes of, let's say, should be that of Nano. Nano presents, it is given as the small letter N, which is times 10 to the power negative, it should be 12. And we have the likes of Pico. Pico presents that of, it is symbolized as the small letter P, which is times 10 to the power should be negative 12. So these are said to be the prefixes, and these are the actually letters that are being used to represent the multiples of zeros on that way. So now let's talk about what we call as the prefixes in the SI units. So we understand that we have, let's say, we can have 2 seconds. Now we can think of incorporating 2 seconds with a prefix. We can have, let's say, 2 nanoseconds. We can have, let's say, 2 picoseconds. Should be that. We can have, let's say, 2 milliseconds. That is okay, where these are the prefixes. And let's say 6 meters, we can have, let's say, 6 centimeters, where that's the prefix. 6 kilometers, that is okay. And 6 millimeters, that is okay. We can have that one. And let's say we can have, let's say, 70 should be, let's say, 70 byte. This is the, we can also have 70 megabyte, or let's say 70 gigabyte. You can have that one. Let's say we have let's say 20, let's say, meters. By the way, we can have, let's say, 20 meters. Actually, we can have it as 20 micrometer, should be that. Let's say 20 nanometer, we can have that one as that. And 20, let's say, a centimeter. And let's say if we can have, so we have several, actually we have several units that we can incorporate with the prefixes. And let's say we can have 2 terabyte, that is okay. 2 GB, that is okay. Let's say 2 megabyte, you can have that on as that. And let's say you can have 7 micrometer, that is okay. And 8 micrometer, that is okay. You can have that one. And 7 nanometer, you can have that one. So at the end of the day, the SI units can also be incorporated with the prefixes. So keep that in mind. So now let us see on how we can apply the concept of the prefixes in the changing of the scales, basically linear scale, area scale, as well as the volume scale. And let's start with the linear scale. What is a linear scale? A linear scale, this is a scale in which the SI units are having the degree power of 1, that is what we call as linear scale. And for instance, we have, let's say, 2 meters. So in this case, 2, it's a magnitude, and the meter, that is the actually SI unit. And what is the power of the SI unit? We have it as 1. So this is what we call as linear scale. Let's say you can have 5, let's say, seconds. In this case, 5, that's the magnitude, and the seconds, it is actually SI unit. And what is the power of the second? We have it as 1, that is a linear scale. We can also, let's say, have it as, let's say, a 6 should be 6 should be that of, let's say, a 6 meters, and this is also part of the linear scale. Let's say 2 should be 20 seconds, this is also part of the linear scale. We can also have, let's say, 2 hours, that is also part of the linear scale, because the SI unit has the overall power of 1. And I can also have, say, for, let's say, 0.2, let's say, minutes, this is also part of the linear scale. And later we can have, let's say, 0.5, let's say, a meter, that is also part of the linear scale. And since the SI unit carries the overall power of positive 1. So that's how you start to understand about the linear scale. And let's say if we have a linear scale that is composed of the prefixes, or let's say have 2 centimeter. Now, how should you have to convert 2 centimeter to meters? As you can see it here, we have the prefix, which is cent, and the meter, that is the SI unit. So if we are to express 2 centimeter to meters, what it does is that we need to eliminate the cent as the prefix. Now, as we are to eliminate the cent, we need to substitute that one with the value of the cent. Therefore, have it as 2 times 10 to the power, and what is the value of cent? Should be negative 2 in the meters. So this is how we should have it. Let's say have 4 kilometers. Now for this case, 4 kilometers in meters, we just have to substitute with the value of the prefix kilo. That is now 4 times 10 to the power positive 3 meter. Should be that. Let's say have 5 in nanoseconds, we can have it as 5 times 10 to the power negative 9 seconds, so have it as that. And let's say we have 6 microseconds, this is the same as having 6 times 10 to the power negative 6 seconds, so have it as that. And let's say if we can have something about, let's say, should be 9,000, let's say 9,000 centimeter, should be millimeter. How should you have this in meters? So in this case, we have to substitute milli with its value. Have it as 9,000, and that times 10 to the power negative 3 meters. So that is, so whenever we are removing the prefix, we substitute that one with the value of the prefix. Now what if we are introducing the prefix? Let's say if we have 2 meters. Let's think of expressing this in centimeter. So now in this case, 2 meters in a centimeter, what you have to understand is that we'll have to divide this one by the value of the cent. That is 10 to the power negative 2. You have 2 here. That will be given as 2 times 10 to the power, and it should be positive 2. So which means having 2 meters, it is the same as having as 2 times 10 to the power should be that of 2 centimeters. And what it does is that in this case, this is the same as having it as 2 times. Now what we have, it's 2 times 1 over 10 to the power negative 2. that is centimeter. Using the laws of indices, this is the same as having 2 times 10 to the power positive 2 centimeters. We'll have it as that. So whenever we are introducing the prefix, we divide that one by the value of the prefix. Let's say if we have 5 seconds, we should have this in, let's say, nanoseconds, let's say in milliseconds or so. How should you have that one? So 5 seconds, this is the same as having it as nanoseconds. But what is the value of the prefix we introduce? Nano, that is times 10 to the power negative 9, and 5 divided by that one. You know, this is the same as having it as 5 times 10 to the power positive 9 nanoseconds. It is the same as that. And how about in the milliseconds? You know, 5 seconds, this is the same as milliseconds, in the sense that we'll have to divide by the value of the mean, which is times 10 to the power positive 3. That will have it as, now should be given as 5 times 10 to the power positive 3. It should be positive 3 milliseconds. So that's how you can have it. And how about, let's say, if we have something about, let's say we have 5 kilometer. Now we should have this in millimeters, let's say centimeters, let's say micrometers, nanometers, and let's say picometers. How should you have it? Now first thing, we need to eliminate the prefix kilo. That will be given as 5 times 10 to the power positive 3 meters. It should be that. And from there we need to express it in millimeters, where we are to introduce the prefix mean. That will be given as the millimeters, but now we should have to divide that one by the value of the prefix mean, and that is 5 times 10 to the power positive 3. Now for that case, we'll have it as, using the laws of indices, this is the same as 5 times 10. Now the powers, now since the bases are the same, the powers just have to subtract. The power of the numerator, which is 3, should have to subtract the power of the denominator. So which means we'll have it as 5 times 10 to the power positive 6 millimeter. We'll have it as that. So this is how we should have to take it from here up to this point. And how about we should have it in actually micrometer? I think you can also do the same way, where we are to express, you know, these 2 centimeter, micrometer, nanometers as the picometer. So try that on. So whenever we are introducing the prefix, you know, we divide that one by the value of the prefix, and whenever we are eliminating the prefix, we multiply that one by the value of the prefix. So that's how you have to get that understand. And now, how about the areas, actually area scale? Let's say if we have, let's say we have, this is a rectangle. Let me have this one as rectangle. Let's say this is a rectangle, and we have it as 2 centimeter, and let's say this is 1 centimeter, like that. Let's say that is the case. Should be 1 centimeter, should be that. And what is the area of the rectangle? Have it as 2 centimeter times 1 centimeter. And of course this is the same as 2 centi square meter square, and this is the same as having it as 2 centimeter square. This is how we basically present the area if we have also the prefix. But in real sense, in all cases, if we have 5, let's say, centimeter square, you know, this is the same as 5 centi square meter square. Let's say 6 kilometer square, this is the same as having 6 kilo square meter square. And let's say we have 7 micrometer square, this is the same as 7 micro square and also meter square. That's the principle behind. So let us see on how we can change the area unit from one unit to another unit. Let's say if we have, so by the way, area scale, that is the scale in which actually the SI unit has the degree power of 2. Let's say we have 2, let's say 2 centimeter square. So how should you have this in meter square if that is the case? So keep in mind that having 2 centimeter square is the same as 2 centi square meter square. We are to eliminate the value of, eliminate the prefixes and to have it as 2 times. What is the value of cent? 10 to the power negative 2, and the overall to the power 2, which is that. To have it as a meter square. Now the powers will have to multiply. We'll have it as 2 times 10 to the power negative 4 meter square. We'll have it as that. Likewise, let's say if we have 5 kilometer square. In a meter square, principle remains the same. This is the same as 5 kilo square meter square. And what is the value of the kilo? Times 10 to the power positive 3, and the overall to the power 2. And times meter square, we'll have it as 5 times 10 to the power positive 6 meter square. We'll have it as that. And how about, let's say if we have something about, let's say 0.7, let's say nanometer square. How should you have that? Principle remains the same. We have it as 0.7. Nanometer should be nano square, and also meter square. We'll have it as 0.7. And what is the value of nano? Times 10 to the power negative 9 to the power 2. And the meter square, that will be given as 0.7 times 10 to the power negative 18 meter square. We'll have it as that. And how about, let's say if we have, let's say we have 6 should be meter square. How should you have it in, let's say, kilometer square if that is the case? So in this case, we are to introduce the prefix after a kilo. That will be given as, we'll have now the value of a kilo to the power 2, since this is the area square. Should be area scale. We'll have it as, should be 6 here. This is the same as 6 divided by, and what is the value of kilo? 10 to the power positive 3. And the overall to the power 2, because this is a scale, should be area scale. 6 divided by times 10 to the power 6 should be in a kilometer square. By the way, this is the same as having a 6 times 10 to the power negative 6 kilometer square. We'll have it as that. So we're using the same concept we discussed about in a linear scale. Let's say if we have, should be 5, let's say, meter square. How should you have this in, let's say, centimeter square, and let's say kilometer square, and say nanometer square, let's say micrometer square, and let's say picometer square. So how should you have that one? Principle remains the same. We are to, let's say, express it in terms of centimeter square. It has to be given as centimeter square, where we are to introduce the cent. That is a prefix, cent to the power 2, since it is the area square, the area scale. And the 5 here, we should have it as 5 divided by, what is the value of cent? 10 to the power negative 2. And our overall to the power 2 centimeter square, that will be given as 5 divided by times 10 to the power 4, should be negative 4. And centimeter square, that will be given as 5 times 10 to the power positive 4 centimeter square. So that is the unit we should have. That is how we should have that in a centimeter square. And using the same principle, we should have it in kilometer square. So that will be given as kilometer square. We should have that and as that, whereby we have kilo square here. That is 5, where we should have it as 5 divided by, what is the value of kilo? 10 to the power positive 3 to the power 2. And take it from here how we should have it, and also do the same way with that one. Now about, let's say if we have this kind of a case, let's say if we have 4 micrometer square, we should have it in a kilometer square, nanometer square, let's say picometer square, millimeter square, and let's say we should have to be thinking of having it as, should be centimeter square. So how do you think we should have that one? So first the thing, we need to eliminate the prefix actually micro, and from there we should have to have it in that way. And also let's finish with what we call as the volume scale. A volume scale, that's now when the unit is having the overall power string. Let's say 2 millimeter cube. This is a volume scale, let's say 7, let's say should be 2 meter cube, let's say 7 meter cube, that is given as that. So this is what we call as the volume scale. And in all cases, if we have, let's say, 5 centimeter cube, this is the same as 5 centicube meter cube. It is the same way we have discussed about the area scale, only that instead of having power 2, we'll be doing with power 3. So if that is the case, try to have the following at your own time. You should have to change the following units. Let's say if we have 2 cubic meter, should be given in 2 cubic, should be in actually a kilometer cube. Let's say nanometer cube, actually micrometer cube, and also picometer cube. We should have it in that. And let's say if we have 5 meter cube, we should have it in, let's say, in the same way as well. So try to have that. And let's say if we have, should be about, let's say, should be 80 centimeter cube. Now we should have it in, let's say, nanometer cube. Let's say should be centimeter, actually it should be decimeter cube, should be the decimeter cube. And that is another prefix. This corresponds to 10 to the power negative 1. You also have that one, let's say millimeter cube as well. So try to have that. So that's how we start to understand about how we can have to, present the number in a scientific notation and take it back, and how we can incorporate the prefixes in different units. So thank you.